measured 0. Chronology, समझ रहे हो? Leviosa, not Leviosa. Were ratios were very interesting to Lorenzo Romano, Amidio, Carlo Avogadro di. Hello everyone, welcome to Catalysis by Vedantu. My name is Pahul and I am an alumnus of IIT Bombay. Today with me you are going to begin your journey of 11th class chemistry, starting with the chapter The Basic Concepts of Chemistry, the very first chapter of NCERT. Now this chapter is very important because it lays the foundation of chemistry for the rest of the chapters. Also, direct questions will be asked from this chapter in your board examinations. Direct questions from this chapter have been asked in the previous years of JEE and NEET. Although the frequency of these questions in competitive examinations is lesser, but still, direct questions can also come from this chapter, and indirectly, I am sure you understand the significance of having a strong foundation. Because if the foundation is shaky, then you know the building is definitely going to fall one day or the other, right? So please pay attention to whatever we'll do in this chapter, alright? So let me give you the expectations of today's class. First of all, we'll have a look at the NCERT's book of chemistry. This chapter, the way it's written, we'll have a look at that, okay? Then we will learn about the basic physical quantities and units. You might have studied this in physics as well. We'll understand what are significant figures, and then we'll go on to the basic laws of chemistry, the law of conservation of mass, different laws of chemical combination and physical combination of different substances. Fine. We'll look at some interesting and important questions as well, obviously, because eventually you're preparing for exams, and in exams you have to answer questions. So practicing questions is very important. And I'll also give you some homework and assignment. Now, today's class is the very first class, so it's going to be more conversational in nature. It's not going to be too stressful. We'll have a lot of fun, and on the way we'll get to know each other better, right? So first of all, as I told you, let's look at the NCERT. I have opened it up for you already. So let's look at the NCERT. The way it's written is very interesting, okay? They've talked a little bit about science. They've talked a little bit about development of chemistry, the philosopher's stone. If you've read Harry Potter, you know what they're talking about. And the introduction of this chapter, the way it's written in the NCERT, is very interesting to read. They've talked about archaeological evidence, remains of Mohenjo-daro. So how, chemists came into picture. How did chemistry evolve, especially looking at it from India's ancient history standpoint. So it's very interesting to read. And that is why I've showed this to you. This particular thing, if you have the book, perfect. If not, this is available online for free. You can go on google.com, search for some basic concepts of chemistry, NCERT PDF, you'll get this for free. Okay, so make sure you check it out, and you have to read it along with me while we are doing this particular chapter. Okay, बहुत ही मजेदार तरीके से बताया हुआ है. They've told it in a very interesting manner. So showing you because it's important for you to read it. Now let's get back over here. Let's come to fundamental physical quantities and understand what's the significance behind them. These are the quantities that we consider fundamental. Why so? We'll understand that in a little while. But the basic fundamental qualities are length, mass, time, electric current, thermodynamic temperature, amount of a substance, and luminous intensity. These are your base physical quantities or fundamental physical quantities. This is the symbol for quantity, okay? Length can be denoted with small l. Mass can be denoted with small m. Time with small t. Electric current with I, capital I. Thermodynamic temperature with capital T. Amount of substance with small letter n. And luminous intensity with I and a nu at the bottom. There's a Greek letter at the bottom. We'll use luminous intensity hardly ever in the syllabus. So no need to worry about this one. But please make sure you write down. Write down the symbols for these quantities as well. This table has been taken from the NCERT, by the way, so no need to fret too much about it. Name of SI unit. SI means Standard International. See, in the world, there are different conventions. Convention means a certain way of things that we follow that everyone agrees on. For example, if in India you have to talk about distance, you talk about it in kilometers, right? Bangalore to Mysore is 150 kilometers approximately. Now, if the same thing has to be done in America, if an American person were to come to India and you tell that person that, okay, the distance between Bangalore to Mysore is around 150 kilometers, that guy will be like, what? I don't understand kilometers, tell me in miles, right? So you'll have to convert kilometers into miles to tell that person approximately, say 100 miles is the distance between Bangalore to Mysore. Kilometers is a convention that we follow in India. Miles is a convention that we follow in America, let's say. The point being that humans tend to use different conventions depending on where they are, depending on who they are. But science is something that deals with accurate things, right? So for science, we need a standard international unit, also known as metric units, by the way. So the standard international units are units that have been established as convention for scientists across the globe. This is what we'll follow, right? So the SI unit for length will be meters. Meter is the SI unit for length. Whenever you have to do calculations, try to do the calculations converting the units of length in meters. Fine. Similarly, the SI unit of mass is kilograms. Do you notice the SI unit is not grams, kilograms. So in questions during calculations, if no unit is mentioned for mass, you have to do the calculations in kilograms. Okay. For time, the SI unit is second. For current, the SI unit is amperes. For temperature, the SI unit is Kelvin. Very important. Later on in chemistry, you will be doing questions where they mention the temperature in degrees Celsius. A lot of students do the mistake of taking the temperature in degrees Celsius and doing the calculation with it. You don't have to do that. You have to take temperature in Kelvin. Okay? Mole is the SI unit for amount of substance. What is this mole, sir? Mole sounds weird. Mole is a rodent. Mole is something that happens on the skin. Different meanings of the same word. But this mole is something that we will understand in the second class of this particular chapter. Fine. So, jo agli class hogi, whatever is the second class, we'll understand what the mole and the mole concept is. And then comes luminous intensity, candela. Never gonna use this. Okay. Hardly ever are you gonna use the unit candela, but anyway, it's there. And if you want to abbreviate these names, these are the symbols that are used. Alrighty. Meter, kilogram, second, ampere, Kelvin, mole and candela. Fine. So make sure you write this table down in your notebooks. Okay. Fine. If you want to pause the video anywhere, you can. If you want to speed up the video and watch it in 1.5x, 2x, do that as well. Okay, whatever feels comfortable to you, please keep doing that. Alright. Now, why are these called the base of fundamental quantities? Well, there are two types of physical quantities. One are basic, fundamental, the ones we've seen. The others are called derived quantities. Derived quantities are those which can be derived from the basic quantities. For example, volume. Volume can basically be thought of as length into length into length or length cube. So we've taken the fundamental quantity length 3 times, multiplied it, and that gives me volume in terms of the unit. Okay, so the unit of volume will be length cubed. Right? For example, we have density. How can I think about density? Density is what? Mass upon volume. In terms of units. In terms of units. What will the unit look like? On top, you'll have the unit of mass. Perhaps kilograms, perhaps grams, depending on how you want to answer the question. Divide by volume. Volume will be what? L cube. Fine. Mass and length, fundamental quantities. So derived quantities are those which can be written as a combination, multiplication, division of your fundamental quantities. So what we choose as fundamental quantities is also a convention. Alright? We could have chosen, okay, in some parallel universe perhaps, we could have chosen volume as our fundamental quantity. So length would have become volume raised to the power 1 by 3. Yeah, the cube root of volume would be length. Maybe in some other universe they do that. So getting the point, the fundamental quantities are also defined as fundamental by scientists. It is a convention to take those quantities as fundamental and the rest of the quantities as derived. Coolio? Fine. Chalo, theek hai. So these are derived quantities and the others are called fundamental quantities for obvious reasons. These conversions of the powers of 10 are a little important for us. Okay, so there are certain numbers out of these which I want you to note down properly in your notebooks. The rest of them you can just have a look at those. Make sure you remember femto. For example, if I write 1 femtometer, okay, small f stands for femto, small m stands for meter. This will be equal to 1 into 10 to the power minus 15 meters. Okay, so if in a question they say what is 1 femtometer or something, 1 femtometer of a substance is taken. So 1 femtometer is 1 into 10 to the power minus 15 meters. Okay, so this one you got to remember. Pico is also something that's important. Picometers, very common unit of measurement for small substances. Okay, nanometers is also important. Nano is 10 to the power minus 9. Milli is very important, obviously. Micro, sometimes you'll see micro, okay, 10 to the power minus 6. Sometimes you'll see micro. The symbol over here for micro is mu. Okay, this is a Greek letter mu, mu. Okay, so whenever you see this means micrometers. 1 micrometer is equal to 10 to the power minus 6 meters. Okay, fine. Everyone knows about centi and deci. Yeah, so these are important from this particular side of the table that you need to remember. Obviously, on the other hand, everyone knows that kilo is important. Kilograms, kilometers, 10 to the power 3. Mega and giga are also important. After that, these are not very commonly used, at least for your syllabus. Okay, so for your syllabus, these femto to centi and kilo, mega, giga are important for us. Now let's come to scientific notation. People over here, if you have to write a certain answer in your board examination, let's say, or you have to write a research paper tomorrow in science, in chemistry, and you have to mention a quantity which is this. Somehow you've measured such a small mass. It's extremely difficult to measure such small masses, by the way. So let's say you have measured 0. Even speaking this number out loud is very difficult, yeah? So there has to be a better way to write it. And I'm sure you've studied that earlier in mathematics, but let's just revise that idea once again. I can write it in a different manner. Okay, I can write it in a different manner. I can write it as 1.66 into 10 to the power minus, now what will come here in this box? 10 to the power minus what? Let's count. Okay, I hope we do it accurately. 1, 2, 3 minus 24. So basically you have to take it back by 24 in order to get this. When we write a weird number like this in such a notation, this is known as using scientific notation. I'm sure you know this already, but just revising this idea for you. 1.66 into 10 to the power minus 24 grams is much easier to speak out loud. It's much easier to write it and understand it as well. Now let's come to something that's even more important. Significant figures. You might have done this in earlier classes while talking about accuracy, precision, etc., etc. You might have done this in mathematics earlier. You might have done this in physics. Maybe you're doing it for the first time. Whatever the case may be, with these examples, we'll understand what are significant figures, why are these important, and these are very important while taking care of calculations. We'll see some calculations as well. And at the same time, my dear friends, this class will be incomplete if you do not study the NCERT after the class. Okay? I as a teacher do not believe in spoon feeding at all. I do not want to give you all the information in one go. I want you to work a little for the information. If you are the one who has to learn how to ride a motorcycle, you have to get onto the seat of the motorcycle and ride it yourself. I can't just put you at the back and keep riding myself. You are the one who has to take the examination, right? So in my style of teaching people, I will make sure that you have to put some effort in order to get some knowledge. Intentionally I will do so that your brain evolves better. I don't want to spoon feed you. Okay? You are 15, 16 years of age. High time you do things yourself as well. So point being that this class will be incomplete if after the class you don't read the NCERT. So you've got to read the NCERT. Alright? Now let's come here. What are significant figures? Significant figures, by the definition of them, now this definition is not that great, honestly. When we'll see the examples, we'll understand things better. But this is the formal definition. Significant figures are meaningful digits which are known with certainty, plus one which is estimated or uncertain. I'll give you a real life example. Let's say you climb onto a weighing scale. You have the weighing scale, you climb onto the weighing scale and they're like, oh, I'm fat. That weighing scale. Okay. So you climb onto the weighing scale and let's say it has a digital display, right? And you climb onto the scale and it says your weight is, let's say, 68.53 kilograms. I'm sure you've noticed that it never comes to the proper weight in the first go. Isn't it? What happens over here is it might display 68.5 and then this number over here keeps fluctuating, right? When you climb on it, will show 68.51, 68.53, 68.59, maybe sometimes 68.6, 68.62, etc., etc. Point being that this number over here keeps fluctuating until it settles down. So let's say after this number settles down, it comes to 68.54. Let's say. So what's happening over here is that these three digits, 6, 8 and 5, these are your certain digits, right? 6, 8 and 5 are certain, but 4 on the other hand is an uncertain digit. When I am measuring the physical quantity of the human body, that is mass, mass is the physical quantity, yes. That's what this machine is measuring for you. That comes out to be 68.5 certainly plus an uncertain digit, that is 4. In the language of science, if nothing is mentioned, if no specific uncertainty is mentioned, then you will consider automatically an uncertainty of 1 in this particular digit. What I mean to say is 68.54, if this is mentioned, a scientist would read this as 68.54 plus minus 0.01 kilograms. There is an uncertainty of 1 in this particular digit over here. 68.55, 68.53, that is the range. That's the range of uncertainty. So automatically, this uncertain digit is considered with 1 unit of uncertainty. Okay? This is automatic consideration. No one will talk about this ever again, by the way. Okay? It's just mentioned in this chapter because you are practicing scientists and engineers and doctors. You should know about it. Right? Chalo. So ये idea है significant digits के बारे में. This is an idea regarding significant digits and how uncertainty is there in the last one. So significant figures are meaningful digits which are known with certainty plus one which is estimated or uncertain. Known with certainty, this one is a little uncertain. Got it? So how many significant figures are there in this number? 68.54. How many significant figures are there? Over here, my dear friends, you have 4 significant figures. 4 significant digits in this particular number. Fine. Now, this was a simple case. Let's come to these examples which are a little more interesting. The first one is very simple. Obviously, how many significant digits? 3. Obviously. Over here, how many significant digits? Some people will say 2, 5, 4, 0, 0, 1, 2, 3, 4, 5. My dear friends, this is not the correct answer. Whenever you have zeros like this, and there is no decimal point that is mentioned, okay? You have zeros like this and no decimal point is mentioned, then over here you have only 3 significant digits. These zeros without the decimal point are not counted as significant digits because they're just 0, okay? Main number is 254, then you've just multiplied it with 100, okay? You can imagine it like that. This can be imagined as 254 or 2.54 into 10 to the power 1, 2, 3, 4. Yes? Do you see I can write this like this? Now over here, how many significant figures are there? 1, 2 and 3. Yes? 2, 5, 4, 1, 2, 3. 3 significant figures and the rest is just zeros that can be multiplied. That is why whenever zeros are not mentioned with a decimal point, if there is no decimal point over here, these zeros are not significant. So over here only 3 significant digits. The more examples we'll do, the better we'll understand. Now, let's talk about 0.009. How many significant digits are there? Some of you must be thinking, sir, okay, 4, definitely wrong. 3, again wrong. There is only 1 significant digit over here, that is 9. 1 significant digit. Why? Again, think of writing it in scientific notation. Okay? Think about writing it in scientific notation. How will you write it? 9 into 10 to the power minus 3. Only 1 significant digit. Now, people, let's come to this example, 20.009. Let's come to 20.009. Now what? Now should we count the zeros? Yes, we should count the zeros over here. This can be written as 2.0009 into 10 to the power minus 1. See, this is important. Okay, this 0.009, this number 9 is important. Let's say you are measuring the weight of some very, very expensive substance. Imagine there's a substance which, sells for, 1,000 rupees for 0.001 grams. Okay, 1,000 rupees for 0.001 grams. Now, if this 20.009 becomes 20.008, 1,000 rupee loss. Do you understand? Okay, so that 0.001 is also important over here. 0.009 mein the 9 is important over here, and this 9 does not exist without these zeros. It starts with a 2, ends with a 9, and zeros are trapped inside. So whenever zeros are trapped inside non-zero numbers, the zeros become significant. Okay, I'll repeat my statement. Whenever zeros are trapped between 2 non-zero numbers, the zeros also become significant. Fine. This is also an imagination that you can think of. So, total number of significant digits over here, 1, 2, 3, 4, 5. Woohoo. Now this one is a weird case. Okay, this one is a weird case. You might be thinking, so obviously we can write this as 0.37 only. You can say that. Okay, if you write it like this, you can think about it. But my dear friends, these zeros are only mentioned, okay? There is a need to mention these zeros only when these are useful, okay? These zeros after the decimal point are mentioned only when they are actually useful. For instance, you say get the weight as, okay, of some expensive substance. You get the weight as 0.37001. Okay, and the answer has been asked only for 4 significant digits. Okay, let's say in their question paper they've asked for answer only in 4 significant digits. So this one you'll have to ignore, right? I can't write it as 0.3701. I can't change the number entirely, right? So basically, these zeros are significant because if I were to write this with more accuracy, okay, if I were to write this number with more accuracy, let's say, then I would maybe have to write something like this. 0.3700127, and when you have to round it off to only 4 significant digits, then you remove this and then you are remaining with these zeros which are important. Because if you did not round this number off, then you would have something concrete over here, right? So these zeros generally come out when you have rounded off a bigger number, and that is why whenever these zeros are written, we will count them as significant digits. So over here, you have 4 significant digits. If these zeros are not significant, you will never write them. ठीक है जी? Whenever zeros are mentioned like this, if I'm mentioning these zeros, that means they are important. That is why we are mentioning them. Okay, so these zeros will be counted as significant figures. Again, as I told you, it's a weird definition, it's a weird concept. Understand this right now, later on hardly you will ever use it, so please just understand what significant digits are and how to count them. People, please keep taking notes. A lot of you who are new to my classes but have been seeing other classes on YouTube will be like, PDF notes, I will get PDF notes, we'll study from PDF notes later. I will make notes from PDF notes later. People, see, first of all, I don't want to waste your time. Whatever notes you have to take it during the class. Okay? You watch it, at slow speed, at 1x speed, while taking notes in 30 minutes, 40 minutes, 1 hour, however long is the class, your job is done. Tomorrow, 6 months later, when you're revising the chapter, you just have to open your notebook, revision done. Okay? The thing that I will teach today in 15 slides, let's say, you can literally write that down in your notebook in 1 page or 2 pages very easily. Revising that will be much easier. When you look at your own handwriting, you'll be like, that is what sir said when I wrote this. Better memory. And as I told you, you are the one who has to take the examination. Please keep taking notes, proper, nice notes. Please don't waste your time by doing rough notes right now, fair notes tomorrow, etc., etc. Please don't. Okay? Just keep taking notes. Trust me, I have been through the process myself. I cleared my JEE Advanced in first attempt, went to IIT Bombay, and my notes helped me a lot. Please keep taking notes. Chalo, coming back to the chapter. Let's see these examples now. Batao ji, how many significant digits are over here? Very simple. 4. Yeah. How many significant digits are over here? 1. But if I have to write this, if I have to show you 2 significant digits over here, then how will I write this? Let's say this 100 number, I want to write with 2 significant digits. There is a way to write it, okay? I can write it as 1.0 into 10 to the power 2. I am writing a 0 after the decimal point very carefully. Therefore, this now has 2 significant digits. You as a scientist, when you're publishing a research paper, when you find a quantity which gives you result, let's say 1.031, okay? You don't want to write 1.031 everywhere. That 31 is not important. So you will write it as 1.0 into 10 to the power whatever, okay? So if you want to write 100 with 2 significant digits, this is how you write it. If you want to write 100 with 3 significant digits, then how will you write? You can write it like this. Yeah, this now has 3 significant digits. If I have to write 100 with 4 significant digits, how will I write it? Four significant digits. So if I am not mentioning the decimal, then you don't count these zeros in significant figures. But if I am mentioning the decimal, then after the decimal, whatever zeros there are, you have to count them in significant digits. Lots of examples will be there in NCERT. Make sure you do them. Even the solved examples, you solve them again. Practice counting significant digits and you will get the hang of it. You will understand it. It's not very complicated once you understand the jazz behind it. Now, let's come to addition and subtraction and taking care of significant figures over here. How many significant digits? 4. How many? 3. How many? 5. 4 significant figures, 3 significant figures, 5 significant figures. What's the minimum number out of these? 3. 3 is the least number of significant figures. Now in the answer that we've gotten out of the calculator, okay, this is how much? 6 significant figures. But technically, my dear friends, this answer is incorrect. It is wrong. We have to report it only with 3 significant figures. That is again a convention. Whatever has the least number of significant figures, we can write only those number of significant figures for the answer as well. So you don't write 4 significant figures for this. You don't write 5 significant figures for this. You have to round it off to only 3 significant figures. Okay. Now how do I round it off? I will write it as 20.8. That is it. 3 significant figures. Answer is done. Now in the same case, similar example, slightly changing the numbers. Let's say you have 9.057 plus 5.80 plus 6.0097. What will be the answer? Basically, I've just increased it by 2 over here. So the answer will be 20.8667. Yes. Now how do I round it off? How do I round it off? Can I write the answer as 20.8 over here? No, the answer now cannot be written as 20.8. See, I have to round it off at this particular point. Yes. Now the next number that we will not write now. Can you see that this number over here is greater than 5? If this number is greater than 5, then you increase this number by 1. To round it off, you will write it as 20.9. Okay. Over here, can you see that this number is less than 5? Yeah. Can you see this number is less than 5? Okay. So the number that we are removing, if that is less than 5, then you write this as it is, 20.8. Okay. Now, also another example that I want to give you. Say you have a number 20.8543. Now what do we do? Now what do we do? This is 5. This is equal to 5. Yeah, so what do we do with this number? Now we have to basically look at this particular number. If this number is even, then you basically let it be. So if I have to round off this particular thing to 3 significant digits, I will write 20.8. But at the same time, if I have a number that is, let's say, 20.7543, let us say this is the number, and I have to round it off to 3 significant digits, I will cut off the number over here. 5 is 5. So now if the cutoff number is 5, let's just call it the cutoff number. If the cutoff number is 5 and this guy over here is odd, then my dear friends, what you have to do is increase by 1. So this to this 20.7543, you will round it off as 20.8 once again. Significant digits. All of this is just convention. This is just a set of rules scientists have defined by their own selves that you have to follow. Okay, if you were born, let's say 500 years back, not 500, that's very recent. Let's say you were born 2000 years back. Then you could have given your own rules, no? Getting the point? So these rules have been given to us so that everything is standardized. If I'm reporting a certain piece of information to you, you should think about it in the same way as I thought about it. Science has to be very precise. Language, on the other hand, doesn't need to be precise. Yeah. On language, on the other hand, let's say a poet writes the curtains are blue. Then whoever reads the poem starts thinking about blue is a symbol of loneliness, and the poet, when he sees curtains as blue, thinks about, you get the idea? Language is not that precise. People think about language in their own ways, but science, numbers, have to be thought in precise ways, and that is why these laws have been defined. If I write 20.8, you should understand what could be the history behind the 20.8. Got it? So all of this jazz is done so that every scientist understands all of these things in the same way. ¿Comprendes? See? Let's move on. Multiplication or division. What do we do over here? Same thing. Okay? Don't worry about it. Same thing over here. 7.9 multiplied by 0.9023. This guy has only 2 significant digits. This guy has 4 significant digits, right? So ultimately my answer should have only 2 significant digits. If I have to round it off to 2, what will this be? 7.1. So this is my correct answer, not this. Now, let's move forward. The boring mumbo jumbo of the numbers is done. Okay. And now we are moving to chemistry's laws. Now, please keep it in your mind that these laws are not given by nature. These laws are given by men. Most of the times, male scientists, female scientists have been in lesser number. Hopefully that changes in the future. But the point being that these laws are given by man. What scientists, what we as a race have tried to do till now is that we get some observations, we conduct some experiments, we observe nature, and we have those observations, and then we try to explain those observations. We try to put them inside a pattern that we humans can easily understand. So what these scientists did was that they conducted different experiments, okay? And on the basis of these different experiments, they observed certain patterns, and those patterns have been written as laws. Alrighty. So the first law that we'll talk about is one of the most fundamental laws that govern this universe. Although this law was modified later by the great Albert Einstein, but let's learn the primitive form first. The law of conservation of mass. It was given by Antoine Leviosa. I don't know how to pronounce this French word. In 1789. Leviosa, not Leviosa. Harry Potter fans out there, let me know. So this is the guy. You don't need to remember the dates and anything. Okay, this date is also not important at all. Don't remember the date. Just look at the statement. Okay, Matter can neither be created nor be destroyed. It can only be converted from one form to the other, and I'm sure you've heard this statement thousands of times. Yeah. Eventually, Einstein realized E equals mc square. So you will study this also in modern physics in your 12th class. But the point is that now mass can be converted to energy, and theoretically energy can be converted to mass. Okay, and this gives us a lot of good ideas about how the universe is formed, etc., etc. But in very old days, mass energy conversion was not known to man. So now the conservation of mass law is basically conservation of mass and energy together. But if we don't consider nuclear reactions, if we don't consider the transformation of mass into energy, then this law, and this works for almost all the processes that are happening on the earth. Okay, law of conservation of mass. Matter can neither be created nor be destroyed. It can only be converted from one form to the other. So how did this guy come across this law? Basically, he observed that no matter how much weight he starts the chemical reaction with, at the end you have the same weight. Then comes the law of definite proportions. Fine. This is also very simple. I'm sure you've done it in earlier classes, given by Joseph Proust. Fine. This is the guy who gave this law in 1794. A given compound always contains exactly the same proportion of elements by weight. What does this mean? I'll explain it with a very simple example. It basically means that if I take water, everyone knows the ratios in which H2O is. So basically you can have 2 grams of hydrogen which combine with 16 grams of oxygen. Yeah, this will always be the ratio. The ratio of mass of hydrogen to oxygen in water will always be 1:8. Okay. Now, this law basically says that no matter where you take water from, if I give you water from my home's water purifier, if you bring water to me from some jungle's waterfall, if a third person brings water to me that he or she has made in the laboratory, all water from everywhere, which is made up of hydrogen and oxygen, will contain hydrogen and oxygen in a 1:8 ratio of weight. Wow, that rhymes. Cool. So a given compound, whatever that compound is, let's say water, simplest example. No matter where that water comes from, water, which is a certain compound, will contain hydrogen and oxygen in only that particular ratio of weight, which again in this case is 1:8. So you can take any compound. For example, you take ammonia, NH3. What's the ratio of mass over here? 14:3. Okay. So no matter where you take your ammonia from, the ratio of mass of nitrogen to hydrogen will always be 14:3. Okay. You take ammonia from anywhere in the world. You generate it in the laboratory, you find it in the natural source, whatever. 14:3. Okay, so that's the idea behind law of definite proportions. Very simple law. You've studied in earlier classes. Let's move on. This is an excerpt that I've taken from from Wikipedia, by the way, and I just want you to read a little bit of it, because thinking about it, we understand that it's obvious, right? Water from anywhere will have the same ratio. Ammonia from anywhere will have the same ratio. But there was a time when different scientists did not agree upon it. Okay, it's written on Wikipedia, and this is just for fun, the sake of science. We're studying it for the sake of science, man. The law of definite proportions might seem obvious to the modern chemists. It seems obvious to us, inherent in the very definition of a chemical compound. Yeah, but at the end of the 18th century, when the concept of a chemical compound had not yet been fully developed, the law was novel. Even scientists did not believe when this law came out. Yeah, a lot of scientists argued with this Joseph guy that no, your law is wrong. Okay, in fact, when first proposed, it was a controversial statement and opposed by other chemists, most notably Proust's fellow Frenchman Claude Louis Berthollet. Science keeps on developing, And whatever seems obvious to you today, hundreds of years ago, it wasn't obvious, right? People had to observe and discover it. And it is possible that today, one of you are thinking of something very significant, which is clear to you, but others might not agree to it. Maybe there's a certain idea that you have, which you understand properly, and it's obvious to you, but for everyone else it's not obvious. And maybe hundreds of years later, when we all are not here on this planet Earth, it's been taken over by the upcoming generation. Hundreds of years later, then maybe someone realizes, oh, this guy was right. Yeah? And that's unfortunately what has happened to all the prolific scientists that have lived to date, especially these ancient ones. In their time, they were never understood. They were always controversial. Anyway, now let's come to the law of multiple proportions. This law was put forth by our very own John Dalton. Saying very own because you've studied his theory of atoms. Yeah. So John Dalton, everyone knows his photo, I'm sure. No need to remember the dates again. So the law of multiple proportions goes like this. If two elements can combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in the ratio of small whole numbers. Small whole numbers is very important, people. See, now that we know atoms, now that we know molecules, now that we know number of moles, etc., now we can imagine that, okay, 2 atoms of hydrogen, 1 atom of oxygen. You can never combine 0.765 atom of hydrogen, right? Because atom can't be divided in terms of chemical equations. Yeah? In chemical reactions, you don't divide the atoms into smaller particles. Fine. Atoms remain atoms. That's the point. So, now that we understand things happen because of combination of different atoms, you can't break atoms, and therefore the ratios will never be like 0.625 atom combines with 0.752 atom. No, right? It will always be 1 with 2 atoms, 5 with 7 atoms. It will always be a beautiful whole number ratio. Back then, it wasn't obvious. People didn't know about atoms. This is the guy who thought about atoms eventually. How did he think about atoms? Because he observed this. Chronology, samajh rahe ho? Do you understand the scientific chronology behind this idea? First observation was that they combine in small whole number ratios. And then Dalton was thinking, they're like, oh, they combine in whole number ratios because atoms are combining with each other. That's when he thought of an atom. It's such a mind-blowing idea if you think about it from the perspective of Dalton. Yeah. So these things might look like, हाँ भाई ऐसे ही तो होगा ना. This is very obvious. Think from their perspective if you can. Anyway, so let's take the examples over here to clarify the statements a little better. So CO. Over here, if I take just their molecular weights, okay. So I can say that over here, I can say 12 grams of carbon is combining with 16 grams of oxygen to give you CO. Over here, I can say that 12 grams of carbon is combining with 32 grams of oxygen. Right? So basically, this element oxygen is combining with the same mass of carbon to give two different compounds. 12 gram carbon here, 12 gram carbon here. So basically what this law says is, if I take the ratio of this, is a very simple ratio. 1:2 ratio. Fine. 16:32, 1:2. Simple ratio. Okay. Same thing over here. You can try it yourself if you want. Okay. Fine. Over here I can write 2 grams of hydrogen combines with the 16 grams of oxygen. Over here I can write 2 grams of hydrogen combines with 32 grams of oxygen. Again, this ratio is a simple 1:2 ratio. Okay. Small whole number ratios. It's obvious to us. And now you must be wondering, sir, how will this come in your examination? Hardly it will ever come in your examination as a question. But even if they ask, they will give you an example like this. They will give you this example where they'll say oxygen combines, they can write something like this, okay? 16 grams of oxygen combines with 12 grams of carbon to give this. 32 grams of oxygen combines with 12 grams of carbon to give this. Please tell what law of chemical combination is this? So they'll give you this example and they'll ask you, okay, tell us what is the law of combination shown over here. Now, obviously, it's the law of multiple proportions. Okay, fine. So that's the maximum extent of question that can be asked from here in your competitive examinations. In board examinations, they might just ask you to write the definition of multiple proportions and cite an example, 4 marks, 5 marks, 3 marks. Got it? So very simple. Again, once you read the NCERT after my class, it'll all fall into place. Now let's come to the most interesting law over here. This is interesting because it's complicated. And if we're able to understand it, perfect. We'll definitely understand it with the help of a very nice example. But let's read it first, okay? The law of reciprocal proportions was put forth by Jeremias Richter in 1792. I know the dates are not important for you to remember, but have a look, okay? Out of the 3 laws of chemical combination, this is the most complicated, okay? 1792. 1803. This law was given later. 1794. The most complicated law was given the earliest, people. Notice, the most complicated law was given the earliest. If 2 elements combine separately, if 2 different elements combine separately with the same weight of a third element, we'll see an example, don't worry. The ratio of the masses in which they do so are either the same or a simple multiple of the mass ratio in which they combine. Let me give you an easier way, or let's say a different way of reading this statement. The different way is, if element A combines with element B and also with C. Okay? There's element A that combines with B, element A also combines with C. Then if B and C combine together, the proportion by weight in which they do so will be simply related to the weights of B and C, which separately combine with a constant weight of A. Let's see this example. Copper with sulfur, copper with oxygen. Okay, fine. Now, over here, when copper combines with sulfur, what is the weight that they combine? Just take their atomic weights, okay? Just take their atomic weight. So, copper's atomic weight is 65.5 grams. It combines with 32 grams of sulfur, right? Everything is in grams, so don't worry about the unit also. This is copper, this is sulfur. At the same time, same amount of copper is reacting with oxygen, right? 65.5 is to 16, right? So the same weight of A is reacting with different weights of B and C, let's say. Over here, let's do one thing. Let's take the ratio of B's to C. Over here in this particular case, when the same weight of A is reacting with B and C, let's take the ratio of weights of B and C, that is 32 is to 16, or simplified it is 2 is to 1. Okay. Now let's come to SO2. Fine. In SO2, what's going on? Sulfur will be 32 grams. Oxygen is also 32 grams. Right? 1 sulfur, 32. 2 oxygens, that is 16 is to 2, 32. So over here, people, this was my B, this was my C. If over here I have to take the ratio of B is to C, what will be the ratio? 32 is to 32, or I can simply write it as 1 is to 1. Fine. Now people, 2 is to 1. Can I simply write it as 2 divided by 1? 1 is to 1. Can I simply write it as 1 divided by 1? I can, right? Now what you have to do, okay? Now what you have to do is you have to take the ratio of these two things. इनका भी ratio ले लो, ratio of ratio. Take the ratio of these two things. This will come out to be a simple number. 2 is to 1 divided by 1 is to 1 equal to 2 is to 1. You can simply write as 2 or 2 by 1 or whatever. Point is, it's a simple number. Read the statement once again. If two different elements combine separately with the same weight of a third element, two different elements combined with the same weight of a third element, the ratio of masses in which they do so are either the same or a simple multiple of the mass ratio in which they combine themselves. This ratio is a simple multiple of this ratio. Sometimes this ratio also comes out to be 1 is to 1. There are certain examples of that also. Okay, so let me give you an example. You do it yourself and you'll understand, okay. Okay? So this particular thing is your first homework of the day. What you basically have to do over here is Na combines with chlorine, Na combines with I. You take the ratio of these two, okay, and then ICl3, you take the ratio of iodine with chlorine, and then see that these two ratios will be a simple multiple. Okay, I'm sure you can see already, but with numbers you see. Now the law of reciprocal proportions also basically gives you the basic idea behind the equivalent concept. Again, if all of these ideas are thought about in terms of atoms and molecules, things become simpler to imagine. But when people used to think about these things only in terms of masses, they didn't even know atomic mass, by the way. They only dealt with these in grams. Okay? Some amount of hydrogen is there, some amount of oxygen is there, some amount of carbon is there, you're combining them. That's all. They didn't know how many atoms are there, how many molecules are there, nothing. So that's why these simple whole number ratios were very interesting to look at. Let's say you're doing difficult calculations with weights. Okay, 37.5 grams of something, 32.6 grams of something else. You combine, you divide, and after dividing all these complicated numbers, you get a simple whole number. So that is the part that was fascinating for these scientists, because they were dealing with complicated masses. After 2-3 divisions, everything became a simple whole number, no matter what mass they started with. Obviously that's fascinating, right? That nature is simplifying things on its own, no matter how complicated we try to make the situation. So that's why these laws back in the day, in the 1800s, they were so important. Fine. Now the last two laws that we are going to study in this class, very simple. Okay, very simple. Law of gaseous volume, again given after observations. Okay, given by this guy, Joseph Louis Gay-Lussac. We'll look at this guy and his laws once again in states of matter chapter later on when we study about the gaseous state. Okay, so the law of gaseous volumes: when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at the same temperature and pressure. Doesn't this look very familiar? Yeah. Law of definite proportions. No matter where I take water from, it will always combine in 1:8 ratio of weight. Over it, just saying the same thing in volume. Okay, if temperature and pressure is remaining same, if it's constant, then simple ratio by volume. This said simple ratio by weight. This is saying simple ratio by volume. Later on, after this thing had happened, people realized that molecules are proportional to volume. Essentially, when hydrogen and oxygen combine, let's say 2 atoms of hydrogen are combining with 1 atom of oxygen, isn't it? Yeah. Or you can also think of it as one molecule of hydrogen gas is combining with half a molecule of O2 gas. Right? So the same ratio will be followed when you talk about volumes. Okay? Same ratio will be followed. What is the ratio over here? Ratio is simply 2:1, isn't it? 2 of hydrogen, 1 of oxygen. 1 of hydrogen, half of oxygen, right? 2:1 ratio. The same ratio will basically be followed by volumes also. Okay? So, if you are trying to make water out of hydrogen and oxygen, if you are taking 20 ml of hydrogen, let's say, okay, then 10 ml of oxygen will combine with hydrogen to give you water. Simple ratio 2:1. So later on people realize that okay, molecules are proportional to volume and that's why this is happening. But back in the day, for Gay-Lussac, this was a great observation he made. Fine. So volumes also combine in simple ratios, and Avogadro's law is what eventually points to molecules. Equal volumes of all gases at the same temperature and pressure contain equal number of molecules. What this means is 5 ml of H2. Let's say this guy has X number of molecules in it. How many molecules are there? We'll learn how to calculate in the upcoming classes. So right now don't worry about how many molecules are there. But say 5 ml of hydrogen has X molecules. If I take 5 milliliters of O2 gas, again this will also have X molecules in it. Okay. If I take 5 ml of argon gas, again this will have X number of molecules in it. And people, since argon doesn't form diatomic molecules, this is just a monoatomic molecule, isn't it? Got it? So over here you can replace this with atoms also if you want. For the case of argon. Okay? So, point being over here that no matter what gas it is, the same volume, provided that the temperature and everything is same, okay? Temperature has to be same. Okay, don't measure 5 ml of H2 at 0 degrees Celsius and 5 ml of oxygen at 100 degrees Celsius. Then, no. But if the temperature is same, then 5 ml of one gas is same in number of molecules to 5 ml of any other gas. That is the law given by Lorenzo Romano Amedeo Carlo Avogadro di Correco di Carreto. Just call him Avogadro, or Amedeo Avogadro is also fine. So this is Avogadro's law. Nice and fun, right? Cool. So people, that's it for today's class. We've learnt about physical quantities, significant figures, calculation of significant figures and why they are significant. We've seen the NCERT a little and we've learnt about these interesting laws. Now from the next class onwards, we will dive into the mole concept. See, in NCERT and CBSE, they write this chapter as basic concepts chemistry, but for competitive examination preparation, for JEE preparation, for NEET preparation, from now on, the name of this chapter will convert into the mole concept. In the chapter of mole concept, we will understand what is a mole, what is atomic mass, what is formula mass, what is molecular mass. Okay? We'll understand what is the mole concept. We'll understand what is stoichiometry. We'll understand what is limiting reagent. We'll understand what are solutions. How do you define the constituents of solutions? Okay? Weight by volume, volume by volume, molarity, molality, etc. And then we'll come to the equivalent concept and then we'll define normality as well. So that's what's going to happen from now on. Some basic concepts of chemistry done. Okay. Now we'll jump into the chapter of mole concept. In NCERT, there's no chapter called mole concept. So whatever we do from now on, is very important because questions from that will be asked directly in your competitive examinations. Mole concept is important for the rest of chemistry also. Fine. So in today's class, basically what you have to do is you have to read about this entire chapter from the NCERT. Okay. Take your time. आराम से पढ़ो इसको. It's a small chapter. It won't take a lot of time, by the way. Read it from the NCERT. I've already told you where to get the PDF from, right? So, once you read the chapter, whatever I have told you today, you read those things again, you'll be like, crystal clear. ठीक है? Comment what's your current favorite song. This is a task for you. I just want to create some fun interaction among us. So don't want to leave it entirely boring. just for fun, okay? Leave in the comments what's your current favorite song. I just want to know. I'll get some new songs to listen to perhaps. Okay? And coming up, as I told you, are these ideas. So in the next class, we'll do mole concept. And we'll do some questions of mole concept as well. Then the third class will be stoichiometry. We'll understand that also in a very fun manner. If you are new to my classes, I hope you enjoy my style of teaching. It's totally different from any other teacher that you've seen, I'm sure. And I will definitely force you here and there to put your own efforts because I do not believe in spoon feeding. That's never helpful for anyone. If you actually want to stand up on your feet, you need to put your own efforts as well. So what I've taught you today is going to be beneficial for you, especially after you read the NCERT of the chapter. Fine. And if you enjoy my style of teaching, make sure you hit that thumbs up button. Stay subscribed to the channel. Hit that bell notification icon. Today, this class was done. Next class will be on Wednesday, same time, 7 p.m. Okay. So I'm going to see you in the next class. Until then, bye-bye. Take care.